In this video, we are taking a look at the very last set of notes for this trimester, which is on 13.4 Infinite Geometric Series. And the first problem you have is a warm-up, and it's a review of the problem we did in the last class. Same problem. We have a patient given the 20 milligram injection, and every day we metabolize half of that away and we get another injection. And so I'm just going to walk through the first one with you to calculate the 10th injection. I think we already did this last class. We want to find S sub 10. Remember, what we're doing is we're getting an injection of 20 milligrams. And then the next day, half of that is gone, but I get another injection. And then the next day, half of the first amount that's left is gone, so I multiply by another half. Half of the second amount is gone, and I get another injection, etc. So when I want to find the amount that's in the system at the 10th injection, I am adding up 10 terms in total. And my initial value is that first injection, which is 20. 1 minus my R value is a half or 0.5, however you want to write that. And I'm going to the power of 10 because I'm looking at 10 injections in total. I'm looking at S sub 10 here. And this is all over 1 minus R, which again is a half or 0.5. And we did this last class and we simplified this down and we got 39.96 milligrams. What I would like you guys to do right now is go ahead and, using the same formula, calculate the amounts at 15, at 20, and at 25, and go ahead and write those into the Edpuzzle. And hopefully, if you did that correctly, what you guys saw was that S sub n appears to be getting closer and closer to 40. The values kept being like 39.99999, etc. So the values are getting closer to 40, but they don't appear to be going over the value of 40. And this can happen with geometric series sometimes. So today, our focus is on the sum of an infinite geometric series. Sometimes we can let it go on infinitely, but we can still find a finite sum. In the problem above, the sum of the series is given by the formula that we used. S sub n equals 20 times 1 minus 0.5 to the n all over 1 minus 0.5, which I'm just going to simplify that to 0.5. So the question is, what happens to the sum as the number of terms approaches infinity? So as n gets bigger and bigger and bigger, what is happening? For large values of n, we are seeing that the 0.5 to the n actually gets really small. If I have 1/2 to the 2, it's 1/4, and then it's 1/8, and then it's like 1 over 100, and then it's like 1 over 1,000. As the denominator increases, the value itself gets smaller and smaller. So as n gets bigger, this 0.5 to the n right here starts to approach 0. It gets smaller and smaller and smaller. As n approaches infinity, 0.5 to the n approaches 0. So basically, if you let this be 0, then that's gone. And all you really have is 20 over 0.5. And that's where we get that value of 40. So sometimes that happens where that second part kind of goes away and gets ignored, and that's how we can find a finite sum for an infinite series. In this example, we call that the equilibrium drug level, and we say the equilibrium drug level is 40 milligrams. Now, this doesn't always work. Here's when it works. If your R value is less than 1. And I'm not talking about if it's positive or negative. I'm just saying the value of R, the number itself. If it's less than 1, then the sum of an infinite geometric series, even though it's going on forever, you are adding pieces that are so small, they don't actually really increase the overall number past a certain point. So the sum of the infinite geometric series converges, which means it goes to a certain number. And you can find it by this formula, S equals A over 1 minus R. Now, I just want to show you where that formula comes from. We did finite geometric series yesterday. And the equation for finite geometric series, I'm writing to the left here. This is the same equation. This is the same equation if you take out the 1 minus R to the n. So the idea is if R is less than 1, then as n goes to infinity, that factor becomes 1 minus 0, which is just 1, which doesn't impact your overall sum. So when we cross out that second factor, that A over 1 minus R is our formula that we use today. So I just want to notice the similarities between yesterday's formula and today's. Now, this only works if R is less than 1. If R is bigger than 1, and again, I'm talking about just the absolute value of R, I'm not talking about positive or negative here, then it doesn't approach a fixed number as n goes to infinity. And so we say that the geometric series does not converge, and so we cannot find the sum. Like it might go to like infinity or negative infinity or something like that. We can't necessarily find it. So we don't have a formula unless the R is a small value. So let's look at two problems here. On example 1, we want to find the sum of each series. And notice that these are two very different problems because in A, this is a finite problem, but in B, this is an infinite problem. Here's what I mean. In A, we're going from I equals 0. So we start at the 0 term and we go up to the 17th term. So that means there are 18 terms in total. Remember, you always subtract those and add 1 because you want to count both of them. So to find the finite sum, I'm using this equation up to the top left, this S sub n1 that I have in the left column. This is from last notes. So I'm going S sub, there are 18 terms, equals my initial term. My initial term is when you plug 0 in for the I there. If I plug 0 in, I get 7 times negative z to the 0, I just get out a 7. So my initial value is 7 when I plug that 0 in. I have 1 minus, my R is negative z here, and I'm going to the power of 18 because I'm looking for S sub 18, and this is all over 1 minus, again, my R is negative z. Now I'm going to simplify this just a little bit. On the top, I leave the 7. When you simplify the top, you're going to do the negative z to the power of 18 becomes positive z to the 18, but you still have the subtraction in front. So you get 1 minus z to the 18. And then in the denominator, though, you have the minus negative turned into a positive, and you get this little guy. So that is my answer to part A. And I don't know what z is, so I can't actually get a numerical answer, but I can get an expression that tells me this. Now, the difference between A and B. A is finite, so I'm using that full formula. B is actually infinite. So instead, I'm going to be using this little bit smaller formula. My sum is my initial value. Go ahead and plug 0 in for I. Take the I equals 0, plug it in, and see what you get. And plug that in for A. And then your R value is going to be the negative z, so plug that in. I'd like you to plug those in and simplify and give me your final answer in the Edpuzzle now. Then we move on to the back page, example 2. We've got this problem about this baseball player, Alex Rodriguez, when he was signed by the Texas Rangers. And this was obviously a long, long time ago. But what happened was he was given a signing bonus for $10 million, and he got $2 million a year for 5 years. So we are giving him $2 million today, and then we're giving him $2 million in a year, and then we're going to give him $2 million in 2 years, $2 million in 3 years, and then in 4 years, that'll be the 5th payment, we'll give him his last $2 million. So that's how we're paying him the total $10 million, $2 million a year for the total of the 5-year span, starting today. So the question is, how much money do we need right now to pay that off? I don't need $10 million, I need a little bit less, because what happens is I'm going to invest my money. I'm going to pay $2 million, and then the rest that I have, $8 million or a little bit less probably, I'll put in the bank, I'll let it get some interest. And then I'll pay $2 million, I'll put the rest in the bank, I'll let it get some interest, etc. So how do we find out how much money we need today? Let's look at each individual payment. Today, to pay him $2 million, I need $2 million because it's today. But what about next year? Next year, if I want to pay him $2 million next year, what do I need today? What I'm going to do is use this formula from our exponential unit. We saw this formula in Unit 3. The amount that I need later is $2 million. what's the amount I have today? So typically in Unit 3, we were given a set amount and investing it and finding out how much it became. Now I'm saying, well, I don't know what the initial amount is, P, that I'm depositing, but I want to have $2 million. The bank is getting 5% interest. And how many years is this running for? Well, if this is my first payment, that's next year. So this is going to run for 1 year. So how much money do I need today? The amount of money I need today is whatever this gives you, 2 divided by 1.05. If I take the 2 million that I need next year and I divide it by 1.05, that'll tell me how much I need today. Because how much I need today times 1.05 would give me 2 million next year. So we can write this as 2 over 1.05. Well, how about the next payment? The next payment, the one that's in 2 years from today. So again, I want to have $2 million. I don't know what the payment is today. And I'm going to let it get interest for 2 years. For 2 years. So then that payment that I need today is 2 divided by 1.05 squared. And this pattern's going to continue. To see how much I need to pay him in 3 years, it'll be a 1.05 cubed. And to see how much I need to pay him in 4 years, it'll be a 1.05 to the 4th. So those values represent each of the individual payments that I need to give him. Well, how do I find out how much money I need? Well, of course, I can just total all these up on my calculator and I can get 9.09. So that tells me I need $9.09 million right now to pay that out. Well, what if this was going on for more than 5 years and I couldn't do it by hand? Then we would need an equation. This is a finite geometric series. Finite geometric series. It is not infinite, so it's not the new formula from today. It's the finite one. I am adding up 1, 2, 3, 4, 5 terms in total. So we are looking at S sub 5. My initial term is this first one, 2. So my A value is 2. Here's where it gets tricky, 1 minus. What is my R value? What do I multiply this first term by to get to this second term? Go ahead and put that in the chat. If you got that wrong, don't worry about it. The answer for the R value is 1 over 1.05. Basically what happens is I'm taking 2 and I'm multiplying by 1 over 1.05 to get this next term. And then I multiply by another 1 over 1.05 to get this next term, and another 1 over 1.05 to get this next term, etc. So my R is actually 1 over 1.05. I put that to the end, which again is the total number of terms, so 5. And I put it over 1 minus R again, 1 over 1.05. And if I type all that in on my calculator, I should get the same amount, the $9.09 million. So let's talk about this concept and let's apply this to an infinite problem. This concept up here is what we call present value. Present value is what do I need now for a future payment? The present value is that P that we saw in the equation, and the future payment, or what I need later, is B, the balance after a certain amount of years. And we deposit it at some interest rate. We use R for that, and we deposit it in the bank account today to have exactly whatever amount I need, B dollars, in the account in the future. We're assuming R is the annual interest rate. We are not doing this with compounding. That would get totally out of control. So we're letting it be an annual interest rate, and we're letting N be the number of years that we run it for. So the equation we saw on the top left, where we said B is P times 1 plus R to the N. This is from Unit 3. We just get P by itself. So to find a present value, you take the balance that you want and you divide by 1 plus R to the N. Now, again, this equation gives you the present value. It does not give you a series. This gave me each individual term of the series, and then I had to add it all up. So what I did in that problem above was we did a sum or a series of present values. So that present value equation is just how you find each individual payment, but then we had to add them all up to see what the total amount was that I needed today. So let's take a look at applying this to an infinite situation. Let's say the bonus said you get $2 million a year, every single year forever, for you, for your heirs, for your kids, whatever, forever. Okay, then what would that be? Then the first payment would be $2 million, and the second one would be 2 over 1.05, and the second would be 2 over 1.05 squared. And this would go on indefinitely. Because it goes on forever, when you see this word, forever, that changes this to an infinite geometric series. And so what we do then is we use the A over 1 minus R formula instead. A is my initial payment. That's 2. R is what am I multiplying by to go from the first one to the second one? I am dividing by 1.05. So I am multiplying by 1 over 1.05. This gives you an actual number. This gives you a number 42. So that means if they had $42 million right now, they could essentially pay out that $2 million a year forever. Now, of course, this is assuming that we get the 5% interest every year. This is not taking into account inflation. So this is not a perfect real world problem, but this is like one example of how this kind of could get applied a little bit. Let's make sure we can do summation notation because that's always hard. So let's write this in summation notation. Let's do summation notation for the 5 payment case and then for the infinite payment case. So for the 5 payment case, that means I'm going from payment 1 to payment 5, I equals 1 to I equals 5. How do I generate each term? I generate each term by the present value formula. So my rule to get each term is the present value formula, which is 2 times my R, 1 over 1.05 to some power. Now, I'm doing I minus 1 because I'm having this start at I equals 1. If you wanted to make this be I, then you could start it at I equals 0 and end at I equals 4. And just check this and make sure that this generates each of those terms in there for you, and it should. If I change this to the infinite version, the only thing you do that's different is you change this top to infinity instead of 5. That is it. Everything else on here is exactly the same.